Le Chatelier's principle, which you may have had a very brief introduction to in your first year chem class, but we're going to go much more in depth to it because now you also understand equilibrium a little bit better. Okay, so Le Chatelier's principle takes a system that is already at equilibrium and adds what we call a stress. A stress is just a change. So you can have a change in concentration, pressure, volume, temperature, and what will happen is that the system will automatically shift to go back to equilibrium. Okay, so you remember from some of our previous videos, equilibrium is a constant, K, but there can be bunches of different equilibrium positions that can get you to that K. Okay, so K, the constant, is the ratio, but the positions can change and get you that same number. We talked about that before. The only way K will change is if there's a change in temperature, and we'll also be going through that today. Okay, so this goes into a couple of other things. If you add a catalyst, we've talked about this before, if you add a catalyst, the rate, like it will get to equilibrium faster, but the constant and the position doesn't change. And then also we're going to have some inert gases in these situations. Inert just means it doesn't react. So if that happens, it doesn't affect anything, not even the equilibrium position. So the best way to talk about this principle is through examples. So we're going to start with this reaction, this generic reaction we have here. A is at equilibrium with 2B. They're both gases, gas phase. It's endothermic, which we'll talk about later on, that will come into play. And the constant is 0.2. Okay? So the first one says, suppose we are at equilibrium with 5 moles of A and 1 mole of B, holding the temperature constant. Okay, so that just means K isn't going to change. If then an additional, so this bullet point is we're already at equilibrium. The system's at equilibrium. Great. If an additional 5 moles of A was added, how would the system respond? Okay, so let's take a look at our choices here. We automatically know that the last two don't apply. Anything that says K changes, we would have to change the temperature, and there's nothing here about changing the temperature. Here it actually even says we're holding it constant, but let's say that wasn't even there. If it's not mentioned, then it's not happening. So we can automatically rule these two out. You can also go ahead and rule out no shift, because if we're changing the concentration, it is going to shift. Okay, that's just a given. So now we just need to figure out if it's going to shift right or left. So there are a couple ways to think about this. Okay, I think the easiest way is, okay, if we need to hold the ratio constant and we're adding more on this side, what needs to happen? We need to get more on this side, right? So if the ratio is going to be constant, because we know K is the same, we need to use up some of the A and get more B. If extra A comes in, the system will respond by moving in the forward reaction, using up some of the A and producing some of the B so that we can get back to that equilibrium ratio. So that means we're going to shift to the right. We're going to shift towards the products. So our answer here is shifting right. So if you want, you can take a look at the math since we know how to do equilibrium expressions, okay? So if we were at equilibrium with 5 moles, so we're assuming a 1 liter container here. I think that's up here somewhere. Yeah, 1 liter container. So when we said 5 moles, that's 5 molar. and 1 mole is 1 molar, okay? If we plug that into our equilibrium expression, we get our K of 0.2. All right, so that's what we just did. That's equilibrium done. Here's the question. If 5 moles of A were added, how would the system respond? So let's calculate Q, because we already know that. We already know Q can tell us right or left. So if we plug in, if we have 5 more moles of A, then our molarity becomes 10. So we have 1 over 10. So Q is equal to 0.1. That means K, that's 0.2, is greater than Q, and that means we shift to the right. So the forward reaction would occur to make this go up and this go down so that we get to our 0.2 equilibrium again. So that's the math behind the answer that we already figured out. So you can easily do that since you already know Q. If you have the kind of brain that really wants to focus on the numbers and the math, you can do that. You can figure out Q and use that information, okay? It is easier for some people, or just as easy, to look at the equation and figure it out, and that is a faster way to do it. So I want to spend some time kind of doing some practice, going over that so that you have that tool in your toolbox as well, not just Q. All right, so let's talk about some more. Now, if you feel like you want to try these, because I'm just going to put them as examples, if you want to try them, feel free to pause the video and give this one a chance, give this one a shot. So we're at equilibrium, and this time we have a 2-liter container. So we have 10 moles of A, so that's 5 molar. 2 moles of B, that's 1 molar, okay? Because we have a 2-liter container. If the container were compressed from 2 liters to 1 liter, how would the system respond? Constant temperature, so we can get rid of anything that changes K, excuse me. Okay? And here's the rule about volume. So if you lower the volume, you know that you're increasing the pressure. Okay, that's a gas law. You lower the volume, you're increasing the pressure. The system will respond by trying to relieve some of that pressure. So it will shift in the direction that there are fewer moles of gas. Okay, and that's really important. It's only gases. We'll talk more about that later. Here we have a gas phase reaction, so we know that both of these are gases. So what's going to happen if you increase the pressure or decrease the volume and therefore increase the pressure, the reaction will shift to the fewer moles of gas. So because we have 2 moles of gas here and 1 here, the reaction is going to shift to the left. So our answer is going to be this, and that's just something that you need to know. If you increase the pressure of a system at equilibrium, the system will move towards the fewer moles of gas. So here, when we increase the pressure by decreasing the volume, it shifts to the fewer moles of gas. It goes to the 1 mole of gas as opposed to the 2. So this is the same reaction. We're just going to use this one for a few of them. Suppose we're at equilibrium, 5 molar and 1 molar. If half the moles of B were removed, how would the system respond? This is probably a great one for you to try, okay? So you might want to pause here and just give it a shot, and then we'll go over the answer. So first of all, the temperature remains constant, so you can get rid of this, anything that changes K. If half the moles of B were removed, if we took away some of the B, then we would need to in order to have the same ratio, we would need to make more B, right? So some of the A will be used up to make more B. So that means it's going to shift to the right. And if you wanted to figure out Q, let's say Q equals, if we take away half the moles, and we're at a 1 liter container, we have 1.5 squared over 5, not 1.5, I don't know why I said that, 0.5 squared. So Q would be this. Since Q is less than K, we know it's going to shift to the right. So again, if you wanted to do out the math, you can absolutely do that. Okay, now let's talk about how temperature affects these systems at equilibrium. So this is the same system, and we've been saying all along it's endothermic, but we haven't really talked about what that means. So before we get to the question, let's talk about the endothermic bit. So endothermic means, and you should remember this from your first year class, endothermic means the system absorbs heat from the surroundings. Okay, so the system uses up heat. What we represent that as in our reactions is we add heat to the reaction side of the product, of the reaction. So here we can rewrite this reaction, this equilibrium expression, as A plus heat gives us 2B. If it was exothermic, we know that that's the system giving off heat, so we would put heat with the product side. Okay? So this is a nice, easy way to use Le Chatelier's principle, which you already know, with an endo-exo explanation. You just put heat into the expression. So if the reaction was placed in an ice water bath, we remove heat, right? So if we remove some of this, we know that if we remove a reactant, the system is going to shift to make more of that reactant. Okay, now this doesn't fit into our K and Q expressions because we wouldn't put temperature in there, but you can use the same basic idea and the rationale we've been using. We know that if we removed some of a reactant, we would need to make more of that reactant to keep the ratio the same, right? So if we pretend that heat is a reactant, we can easily just think of it that way. So we know it's going to shift to the left, right? Because we removed some of a reactant. So I'm going to get rid of anything that doesn't say shift to the left. But this time we can't just get rid of anything that changes K, because when temperature changes, K does change. Okay? So we know that it's going to be this one, because that's our only option. But let's talk, what if we had had shift left K becomes smaller, shift left K becomes bigger? What if that was our two options, okay? We wouldn't be able to make it this easy. You need to think back to one of our videos from last week where we know that if K is bigger, it favors the products. And if K is a smaller number, it favors the reactants. So here, if we're favoring the reactants more, okay, because it's endothermic, so we're going this way if we make it colder. So if we favor the reactants, we make K smaller. If we were going the opposite way, like if we had heated up the system, then K would get bigger. So same system. If we added an inert gas such as He, like helium, if we added an inert gas holding temperature constant, total pressure increases, what would happen? So we already said if you add an inert gas, nothing happens, okay? So nothing, no shift, no change in K, nothing. The total amount will increase, the total P will increase, but we don't have total P in our equilibrium expression, right? We don't have total P anywhere. We have the partial pressures of the individual gases. So in our equilibrium expression for this, if we were to do it as Kp, we would have pressure of B squared over pressure of A. We don't have total pressure anywhere in there. So an inert gas is not going to react with anything. It doesn't change the concentration of A or B. So it doesn't change the partial pressure of A or B. So there's no change here. Okay, nothing is changing. We don't put He in there because it's not reacting. So there's nothing to have it do. So no change. No change in K because the temperature is the same. No change in the shift because the partial pressures aren't changing. So that's why the inert gas won't change anything. All right, so now we're going to change it up a little bit, and we're going to use still gas phase, still endothermic, but we're going to do X and Y here. And the major change here, because it's still generic gases, the major change here is our coefficients. So before we had A gives 2B, now we have 1X gives 1Y. Okay? K also changed to 5. So here, if the container was increased in size from 1 liter to 2 liter, how would the system respond? So let's think about that. Temperature is constant, so we can get rid of these two. K is not going to change. Whoops. But let's talk about what happens when we increase the volume. When we increase the volume, that means we're decreasing pressure. And our rule for pressure is that if you increase pressure, you go towards the fewer moles of gas. If you decrease pressure, you go to the greater moles of gas. So in your reaction, you would figure out which one has more moles of gas. They're the same. They both have coefficients of 1. They're both gases. So that means there's no change. Okay, if they have the same amount, the same moles of gases, then the volume change or the pressure change doesn't change the equilibrium system. There's no shift. Now we did something similar to this with our A gives 2B reaction, and we did have a shift because those did not have the same moles. So now let's take a look at this one. If KEQ is 3.5 at 600 degrees Celsius and 45 at 100 degrees Celsius, is the reaction exothermic or endothermic? So what that is telling us, if K goes up, if it goes from 3.5 to 45, that means our reaction is shifting to the right. We are favoring the products more because remember, a higher K value means you favor the products. So we're favoring the products more, okay? So now let's take a look at what side of our reaction heat would be on. If we're favoring the products more after we cool it off, because we went from 600 to 100, okay, that means we lost some heat, and that made us go towards the products more. So that means we would have heat on our product side, right? Because if heat went down from what we said before, we would need to go towards the products to produce more of it. So that must mean we have an exothermic reaction here. Because if heat is on the product side of the reaction, it's exothermic. So let me just explain that all again, because that was a lot. So the first thing we know is that the reaction is going towards the products more because we go from 3.5 to 45. If there's an increase in K, we're going to the products. The next thing we know is that we did that when the temperature went down. It went from 600 degrees Celsius to 100 degrees Celsius. In order for us to favor the products when the temperature goes down, heat needs to be seen as a product. That's what would make the reaction shift that way. If heat is a product, that is exothermic. All right, for the reaction above, which I hate when my arrows don't transfer to that, the total pressure is 6 at equilibrium. What will be the total pressure when the volume of the container is doubled? So let's figure out what that means. When the volume of the container is doubled, the pressure decreases. When the pressure decreases, the equilibrium or reaction shifts towards more moles of gas. Okay, and it tries to get it back up to 6. So the pressure, if the volume was doubled, the pressure would initially would go down to 3, because when the volume is doubled, then the pressure is halved, right? But the system, because it's an equilibrium system, is not just going to take that, okay? It's going to try to get it back. It's going to go towards more moles of gas. It's going to shift to the left because we have more moles of gas over there. However, it's not going to get perfectly back to 6, okay? There's going to be a different ratio that hits our equilibrium position. So just like with KC, we can have that same ratio with different positions here. And that's what would happen. It would shift, it would definitely increase over 3, but it will not be able to get all the way back to 6, which was perfect, like, equilibrium before. So we're going to say it's more than 3, but less than 6. Okay, so here's another pressure question. Which direction will the reaction shift when the pressure is increased by reducing the volume? So here, if you reduce the volume, you increase the pressure, and that means you're going to shift towards fewer moles of gas. And at first glance, you might say, oh, the same moles. We have 3 on this side and 3 on this side, so no shift. But that's not the story. Look, this one is a solid. We said fewer moles of gas. So it is going to shift to the left because we only have 2 moles of gas on that side. Okay, so you have to pay attention to these little symbols in the volume pressure situation. So it will shift to the left. So same reaction. What will happen to the moles of C if a small amount of A is added to the reaction vessel? So we're adding a little bit of solid here. If we add in one of our little heterogeneous equilibrium things a little bit of solid, nothing's really going to happen, right? That's not in our expression, in our equilibrium expression. Okay? If we added enough that it changed the volume and changed the pressure, that's a different story. But here, we're just adding a small amount. We can assume that the change in volume would be negligible. So we can say there will be no change in K because we know that there's temperature. But the moles of C will also stay the same because there is no change when it's just a small amount. Like if you dumped a whole bunch of solid in there, that would then change the volume and that would change the pressure and that would make everything shift. But here, when you're just adding a small amount, it's not going to change anything. But let's see what happens if we change B instead of A. A was our solid, B is a gas. Okay, if more B is added, more gas, that does change the pressure. Okay, so K is not going to change because temp is constant. So that gets rid of this one, this one, this one, and this one. So what will happen to the mass of A if more B is added? Okay, if more B is added, that does change our equilibrium because it will change our expression. So like if we had our Kp expression, we would have the P of C to the third over the P of B to the second, okay? And if we increase the amount of B, we're going to increase that pressure of B. So what will happen is that our reaction will shift this way. In order for that to happen, we need to use up some A to combine with the extra B to form more C. Okay, so again, because this is a gas instead of a solid, because B is a gas, we will end up shifting. So that means we're going to use up some A. So we go with number 4. Mass of A will decrease because we need to use some of it to get back to equilibrium. So when you add some of the solid, nothing changes, but when you add something else, the solid is affected. Here is just a quick summary about solids because that was really new. And then the same applies to pure liquids, meaning not solutions. Okay, if they're solutions, we go to the concentration, all that business. But if it's a pure liquid, like liquid mercury, for example, the same deal with a solid will follow the same rules as pure liquid. If you add a little bit of it, it does not cause a shift. But if other factors change that causes the shift, it will be affected. All right, so that's it for Le Chatelier.